For this problem, we have the following information given to us. So summarizing that, we have given the balanced chemical equation, now for this particular equation, its value of K sub C at 700 degrees Celsius is also known, so we copy that one as well. K sub C is 0.534 at a temperature of 700 degrees Celsius. And to this particular reaction, we are initially given this number of moles of hydrogen, 0.0817 moles of it. Same with our carbon dioxide as well. Its amount is also given to us initially. And all of this is loaded into a 1-liter container. So with all of this information given to us, we are now being asked to determine how much of the hydrogen will be left at equilibrium. So in mathematical terms, we write it as the following. And to solve this, we have to first look at the value of our K sub C, try to see where it falls in its value so that we can know just what exactly we should be doing. Now K sub C, as you could see, has a value of 0.534. It's not so very large nor very small. So from our discussion, we recall that we have the following steps to use once we have a K sub C, not too large or not too small. So the first thing to do would be, if we're not given the concentrations in molars, we have to do that one first. So for hydrogen, the initial concentration of that one should be about the same as the initial concentration of carbon dioxide. That will be equal to 0.0817 mole in a 1-liter container. Now plugging that into the calculator gives us the molar concentration of these, which is 0.0817 molar. With the concentrations already known, we can now set up the ice table according to step 2. So we just copy the balanced chemical equation that we have right here. So copying that one now, we have the following. So that's hydrogen plus carbon dioxide reacting to form water and carbon monoxide. Initially, we start off with the following concentrations of our reactants. So namely, there is 0.0817 molars of hydrogen, same with the carbon dioxide. And as for water and carbon monoxide, there is no mention of them initially, so we just simply assume that there are none of them initially present. As this reaction proceeds, some of the reactants, let's call that amount as X, will be used up. So the amount of hydrogen will decrease, same with the amount of carbon dioxide. to be able to form some water and some carbon monoxide. Now summing all of that up, the initial concentrations plus the changes in their concentrations should give us the concentrations of these species at equilibrium. So at equilibrium, we have for hydrogen and carbon dioxide the following values. And for water and carbon monoxide, their equilibrium concentrations are given as equal to X. So step 2 is already done. With that, we are now ready to write our K sub C expression according to step 3. So for this particular reaction, the K sub C value, or the K sub C expression rather, is given as the concentration of water multiplied by the concentration of carbon monoxide divided by the concentration of hydrogen times the concentration of carbon dioxide. K sub C is already given to us at 700 degrees Celsius. So we recall from the given, K sub C is 0.534. So we substitute it here now. K sub C is 0.534. And from our ice table, we can now write the following. For water, we have X. Carbon monoxide, its equilibrium concentration is also given by X. And that is divided by the equilibrium concentrations of hydrogen and carbon dioxide. Now if you notice, the right side of this equation is a perfect square. So what we can do now is we can try to get the square root of both sides in order to be able to solve for X. So getting the square root of the right side gives us the expression X divided by 0.0817 minus X. And plugging this into the calculator, the square root of 0.534 is going to be equal to 0.7307. Now multiplying both sides of the equation by the denominator allows us to further simplify the rational expression on the right side of our equation. So we have 0.7307 times 0.0817 minus X now equal to X. Distributing 0.7307, we get 0.05970 minus 0.7307 X equal to X. And combining like terms to one side, we're left with 0.05970 equal to 1.7307x. Now finally, we are now able to solve for our x here. X is then going to be equal to the quotient 0.0597 divided by 1.7307, or using our calculator, x is then equal to 0.0 0.3449. We have not made any simplifying assumptions to our computation, so x should be exactly correct if we have done all these steps correctly, that is. So therefore, to compute our required quantity, we now have the following. So at equilibrium, the molar concentration of hydrogen is, from our ICE table, equal to 0.0817 minus x. And substituting the value of x we have just been able to compute, we get the following value. So the molar concentration of hydrogen at equilibrium is equal to 0.0472 molar. Now finally, to get the number of moles of hydrogen left at equilibrium, we have to multiply the molar concentration by the total volume of the reaction vessel. So the number of moles of hydrogen that is left at equilibrium is equal to the molar concentration times the overall volume, and that is then equal to 0.0472 mole.